original date. So what want you to have a look that I am going in the sequential order in the book. So if you really want it, you can look at the book. Otherwise, I will post the notes on the Canvas. Okay, so this is also from the book. So the radial component of radiated power density of an antenna is given by so this is the radiated power density. It has the unit vector R and some value, and we want to find total radiated power. Let me just check that. Is it they are saying real power or just the power? Can you check in the book? It says real power or just the power? Total radiated power. Yes, that's fine. Okay. Okay. So we know in the solutions, we know that we have developed the relationship of P-rad is equal to dA, right? Where R, like the N is the normal vector that is pointed out from the, like the surface area you are considering it. Okay, so normally when we take this thing, we say that this is AR, R squared sine theta, d theta, d phi. And we will plug this in. Okay, and what do you think our angle limits should be? I will come back to that as well. So if you are not given any range of angles, you will say that you will take the whole range. Okay. So what do you think our angle limits should be? Let's say, what do you think theta should be? Aaron?
Would it be like 0 to 2 pi?
Theta.
Would theta be
Why
part
do you
of
think
that?
0 to 2 pi? Yes, go ahead. What?
Would theta be part, like one of the bounds then? Because I was thinking of just putting in like the whole unit circle.
Yes, whole limit we have to put, but we have different limits for theta and pi. Oh, theta and phi, sorry. So you are saying for theta, we will put 0 to 2 pi, right?
Yeah.
Okay.
And then would the other one be 0 to pi?
Okay. When you say theta, you meant the component that is making angle with z. If this
Yes.
is, so you meant this is theta, right?
Yeah.
Okay. Parker, what do you think?
I agree with that.
Okay. Shane, what do you think?
Theta only goes from 0 to pi, and phi goes from 0 to 2 pi. Other than that, I agree.
Why? Why do you think it's that?
Because phi is the one that goes around the z-axis, so that goes the full 360 degrees around, while theta only goes from the positive z-axis to the negative z-axis. So that's only 0 to pi.
Yes. Yes, that's right. But it's hard to understand. I understand. It's fine. So let's go through it a little bit more. So what we are saying that what should be the angle of theta, okay? So what Shane is saying that theta varies or this component varies 0 to pi, right? And if there is a phi, this will vary in the like the 360 angle, that is 0 to 2 pi. So the purpose is to make the whole sphere. Okay, so if we do that, we will make the whole sphere. So we do not need to put theta as 0 to 2 pi. Okay, we do not need to put theta is equals to 0 to 2 pi because it is already serving our purpose that if we change our theta from 0 to pi and our phi from 0 to 2 pi, it will automatically create a sphere for us. Is it clear or is it still confusing? Krupa, what do you think?
I think it's clear.
Okay, and if you noticed last time, when we did angles in the like the FICO, we were also putting for theta we were putting 0 to pi, and for phi we were putting 0 to 2 pi. So when you will be doing next time, you will notice that far field or the sphere will complete if you make 0 to pi and 0 to 2 pi. So that's what I'm going to do. So 0 to pi and 0 to 2 pi. So they will multiply with each other and produce 1. So we will have r square will be canceled with r square. And we will have a naught sine square theta, d theta, d phi. We know that sine square theta is equal to 1 minus cos 2 theta divided by 2. Okay, so I will replace this. And I will make it I can also write so this will become 2 pi pi by 2 minus sine 2 theta by 4, 0 to pi. Somewhere up, I lost a naught. I will write it everywhere. So if you want me to scroll up, just let me know, okay? So this is the radiated power, and you can see it's a real component. It's not having any imaginary component in it, right? So this is a total radiated power for antenna. Okay. Are we good about this? So in the example problem, what you have done is just you were given average power density in terms of theta. This is not in terms of phi. And you just plug this in your radiated power formula, and you will solve it according to like the equation. Another thing is that this is also important to know the limits, that you know that your theta will vary from 0 to pi and your phi will vary from 0 to 2 pi. Okay, and that's about it. Are we good, Sarah? Sarah is here? Okay.
Professor, I actually have a question.
Yes.
I'm not sure if I missed something, but did you pull out an extra phi, or when you pulled out the integral of from 0 to 2 pi?
Oh, yes, that's right. 1 minute. I should not write it like this. I should write it like this.
Okay.
Yes?
All right, thank you.
Yeah. In my mind, I did the integral, but I have not actually. Yeah, thanks for pointing it out. Okay. So we are good about this? Okay. So I am actually, this radiation intensity is very, very near to like density. It's just another way of defining it, but we need to define it because we will use it like in the future references. So I am just writing it. So radiation intensity. Okay, so radiation intensity it's actually another form of radiation density, but we want to define it because we may use it. So radiation intensity in a given direction is defined as the power radiated from an antenna per unit solid angle. What it means that we are defining radiation intensity as U. It is actually equal to R square W rad, or average power density. So we are taking the factor out of R in it. So radiation intensity will be only dependent on your theta and phi. It will combine its R square factor in radiation density. So that's the difference. So it's U is equal to radiation intensity, and its units are W by unit solid angle. And we know that W is radiation density, W by meter squared. Okay, so if I defined radiation intensity in a far field of an antenna, so it will be only defined as theta and phi. It will not have R component in it. So, okay. So we know that it is equal to R squared W rad, where we know that our W rad was 1/2 E, a real part of E cross H. I'm just writing this because it will lead us somewhere. I'll need to confirm that it is the same. E cross H conjugate. Okay. It's not in your book, but I'm just giving a little bit of the background, what it is. So in the far field, we think that it's a real component of electric field, okay? So I will say that, I think they have not mentioned it, but it's fine. So I will write it like H is equal to E over eta in your far field, okay? So it's a big approximation of the magnetic field in far field. We are not talking about directions yet, okay? We are just saying that H, like the magnetic field vector, is equal to electric field vector by eta. And I will define what eta is, but it's a big approximation for the far field, okay? And E is E in the far field. So we know that it's real, so we will replace this thing as R square 1/2 E square by eta. Okay, and of course they both are dependent on, yes, I think R, theta, and phi.
Dr. Khan?
Yes, yes.
Well, what's in the denominator?
1 minute, sorry. I know you may be lost, 1 minute. Yes, now you go ahead. What you're saying? Sorry, what you were saying, Andrew? You were
What's, it's Keith. What
yes,
was in the denominator?
eta. It's a Greek letter word, but I will tell you what it is, okay? But I'm just writing that this is the expression that you will have for radiation intensity. I will tell you what all this is about. But what it is, I will write this here. So eta is a quantity that is called intrinsic impedance of antenna, and it's a constant. Okay, I don't exactly remember, but I think it's E naught by mu naught or something like that. But we will come to that. Its value is 120 pi, but it's a constant value. It's an intrinsic impedance of antenna. Okay, and so we are saying that we have two components, theta and phi, because in radiation intensity, or we are actually having two components, E theta and E phi, which are far zone electric field components of antenna. And if we define E or theta phi, it's far zone electric field intensity or component of antenna. I know this is something that you are maybe completely lost the track of. So we will get this back, okay? Let's take a look again, what we are talking about. So we are good till here, R squared W rad, right? All of us are good till here, right? Now we need to think next what it is, okay? So we know that our W rad was half real part of E cross H conjugate. We know that this is fine too, right? Now we are just approximating our expression in terms of far field, okay? And we know that because in the far field, everything turns into real, so people can make a lot of approximations, okay? So what they did, actually, they said that this magnetic field vector, irrespective of its direction, its quantity is actually E over eta in the far field, where eta is some constant value, okay? So they are saying that H can be defined in terms of E. So that's what they said, that E over eta is actually H in the far field, okay? Then if you think about it, they said that because E field is already real in the far field, then we don't have to write like the tedious expression, real part of E cross H. So that's why they did like this. R square by 2, because this will be R square by 2. And if we are writing it in the far field, we will be write E into E by eta. So we will be just doing R square by 2 eta E square. Okay, so we are good till here, right? Are we good here? Keith, what do you think?
Yep, I'm following along.
Okay. Now we need to listen that what E is, what components E has in it. We know that we are talking about spherical coordinates. So E will have R, theta, and phi in it, right? So we can just totally write it like this, that E is the function of E, R, theta, and phi. And this would be R square plus, okay. And let's just write this one like this. So someone asked me when we were doing wave interactive questions that can E has multiple sections in it? I said yes, E can has multiple components in it, right? E can has X component, E can has Y component, E can has multiple components, right? That's what we said. Similarly, here, E has two components. E has theta component and E has a phi component. It's the same as that you were seeing that E was having X component and E was having Y component, right? So that's why in this expression, you can write it as E theta R theta phi square plus E phi R theta phi square. And let's say do this, or maybe write it somewhere else. I will write it here. So E has two components in it, like you were seeing X and Y components in E. Okay. And when you will make it multiplied by R square, its R square dependence will be gone, like you were seeing in intensity. So you can just write it as okay.
Wait,
Are
what
we
happened
good?
to the R
Yes,
component?
yes. Go ahead, Andrew.
I'm sorry. What happened to the R component?
What?
The R was removed. I was wondering why.
Yes.
Oh, it could be factor. Okay, never mind.
No. So R is removed like this here. You were saying that when you multiply R with WRAD, its R dependence is gone, right? Similarly, here, when you multiply it with R, its R dependence will be gone because you are incorporating it inside the R factor. So this is about 2.12 equation. I just wanted to tell from where it comes from. So it should not look like to you, oh, it's something very difficult. It's not. It's actually the simple approximation of the far field. Okay. So thinking about this, that it's the same as radiation power density, I can also write P rad as, which was previously NDA, right? Let me confirm it. Yes, WRAD dot NDA, which was previously that. So if I am just writing in terms of the power density, which was this, I will write it. Okay, so it will become this. So, okay. So let's solve an example, and that is example, the same as example 2.2. I will just see that in terms of intensity, how it will differ. Okay. So the question is that for the problem example 2.2, find the total radiated power using this equation. Okay. So let's see, it's the same example, but we need to find total radiated power using this equation. So let's see. I think nothing will change except that instead now your W rad was previously will become now and when you will solve it, it should give you the same answer. Like when I'm solving it, because I will reduce, I will just write this thing. So it will be but if you closely look at it, we have removed one complexity from this, from the power density formula. Can you tell what it is? Can you figure out that what was the complexity in the power density formula that we are not having it here?
would it just be the AR vector?
Yes. So we do not have to think about AR vector here. Like we do not have to think about unit vector here, right? So it's independent of unit vector because we have this theta and phi, but we are not doing what you should say we are not representing radiation intensity in terms of direction here. Okay. Okay. And one more thing I want to say here, that if you see the previous lecture in which we have defined the radiation or the power density of the isotropic radiator, I will write it here from the previous lecture. It is it was this. So the radiation intensity will be for isotropic radiator. Okay. So if I just quickly show you something, 1 minute. So are we done with the writing? Can I share my screen?
Yes.
Okay. So can you see this thing? So this is the radiation intensity of your one of the antenna, but how this is plotted, they just follow this expression with the changing theta, okay? So it's just the plot of this expression in terms of this. Okay, so you might be wondering how these plots are coming. I mean, how you are building these plots. So they are just the plot of radiation intensity here. Okay, and similarly, this one is as well. Maybe we will do these plot by ourselves as well, but that's the plot of radiation intensity. Okay. Okay, I wanted to discuss one more thing with you. 1 minute. Hmm. It was regarding the waves. Let me share the screen. So it's just the fun facts or the things we don't know. It's not serious, but it's just this that the standing waves are, we know that they are the stationary points and they change without any motion, right? So in these waves, we see the combination of some waves that are traveling, and if we get the traveling part out of the oscillation part, we will see some standing waves, right? And then there are two kinds of waves that we have seen. One is the traveling wave and one is the standing wave, right? So traveling waves are in which the crest and trough shift their energy to the next particles and they move on. In the standing waves, the crest and trough do not shift their energy to the next particle, but they oscillate at the same point, right? So, but I don't think we talked about this, but there are two types of waves. One is longitudinal wave and one is transverse wave. In the longitudinal waves, your particles change in the direction of motion. Like the spring has this longitudinal effect in it. Sound waves are longitudinal waves, but the transverse waves, in the transverse waves, like the particle moves in the perpendicular direction of the direction of motion. Okay, so that's the transverse waves. So if we may not use the longitudinal waves much, but it's just for our understanding that what are the longitudinal waves. So if you see, this is a sinusoidal signal in which your particle moves from one place to another, and it is actually transferring its energy. And the difference happens when there is a less amplitude, less energy will be transferred. When there will be more amplitude, more energy will be transferred. So with respect of the amplitude, energy can be measured. Okay. And this is the difference with the longitudinal and transverse waves. So if you see longitudinal wave, how you can see the disturbance is in the direction of the propagation. And here the disturbance is in opposite direction of, like in perpendicular direction of the propagation. Right? And similarly, this is the longitudinal waves and the comparison of their change. Okay, this, I think this we will talk maybe next time. Okay, so I think so. I wanted to talk a very, very interesting thing here, but I think I will keep it for next time. And that's about it, okay? So there is a minute paper over there, solve it, and I will also extend the deadline of the design block. You will have next design block to do the assignment, and that will be due after that assignment, okay? And other than that, for now, we are not having any homework. I will give your homeworks back soon that you have submitted, and just let me know if you do not understand anything. If you want me to review anything, if you think we should review the derivation that we have done before, so let me know in the minute paper, okay? Sounds good?
Professor, are you able to upload the notes that like the example problems that we did in class onto Canvas?
I uploaded last lecture because I thought that it was a little bit hard, but you think that I should upload others?
At least with this one, because I plan on going back to like go over it again just to make sure I understand it.
Okay, yeah, I will do that.
Thank you.
Okay. Okay, then sounds good. Today we are closing early. Okay, thank you.
Thank you.
Bye.
Have a good one.
Thank you. Have a good one.
Professor,
Yes,
I just want to let you know, I signed up for the office hours so we could further discuss the internship opportunity.
yes.
So
So you got the time?
yeah, I scheduled for it was 11 to 11:30.
Okay, yeah.
So
Okay,
just wanted to let you know.
yeah, thank you.
Okay, see you then.
See you there.